Application whitelisting theory and setup. Application whitelisting is a very effective protection mechanism, but it can be difficult to manage and deploy at scale, and is not commonly deployed by larger organizations. A typical Windows-based application whitelisting solution is installed as either a filter driver or through the hypervisor. In this section, we'll discuss the theory behind these implementations. Application whitelisting theory. The native Microsoft whitelisting implementation leverages a kernel mode filter driver and various native kernel APIs. Specifically, the Microsoft kernel mode PS set create process notify routine EX API registers a notification callback, which allows the execution of a provided kernel mode function every time a new process is created. Application whitelisting software uses a custom driver to register a callback function through this API. This callback is then invoked every time a new process is created, and it allows the whitelisting software to determine whether or not the application is whitelisted. If the software determines that the application is allowed, process creation completes, and the code will execute. On the other hand, if the application is not allowed, the process is terminated, and an error message may be displayed. As the name suggests, whitelisting software will block everything except applications specifically listed in a configurable rule set. Microsoft provides multiple native application whitelisting solutions. Prior to Windows 7, Microsoft introduced the Software Restriction Policies, or SRP, whitelisting solution. It is still available, but has been superseded by AppLocker, which was introduced with Windows 7, and is still available in current versions of Windows 10. AppLocker components include the kernel mode driver appid.sys and the appid service user mode service. Appid service manages the whitelisting rule set and identifies applications when they are run, based on the callback notifications from appid.sys. Microsoft released a new type of application whitelisting solution with Windows 10, which is enforced from the hypervisor, subsequently operating at a deeper level than kernel mode solutions. Originally introduced as DeviceGuard, it was recently rebranded as Windows Defender Application Control, which performs whitelisting actions in both user mode and kernel mode. Now that we've briefly discussed the basic application whitelisting software theory, we'll begin configuring whitelisting rules for AppLocker, one of the more commonly deployed solutions. Note that AppLocker is only available on Enterprise and Ultimate editions of Windows, which excludes Windows Professional and other versions. Third-party execution. As previously stated, AppLocker only enforces rules against native Windows executable data file types. If a third-party scripting engine like Python or Perl is installed, we could use it to very easily bypass application whitelisting. To demonstrate this, we'll create a small Python script and execute it. The output shows that AppLocker may easily be bypassed through a third-party scripting engine. But of course, it must be previously installed, which is rare in most traditional environments. Bypassing AppLocker with C#. We have successfully bypassed AppLocker's PowerShell restrictions and have executed arbitrary managed C# and PowerShell code through install-util. However, this relies on the existence of a single binary, If install util was blocked by a deny rule, this technique would fail. Let's improve our tradecraft by building another AppLocker bypass in C#. In addition to providing an alternative bypass method for C# code execution, this process demonstrates basic techniques which could aid future research. Discovering a bypass is not completely trivial, so we'll divide this process into a number of steps. Wrapping up. In this module, we have outlined the concept of application whitelisting and bypassed AppLocker, which blocks much of our previous tradecraft. We have introduced various techniques to bypass many types of AppLocker rules, ranging from simple bypasses to much more complicated bypasses that leverage other native, trusted, and undocumented applications. We have also updated our tradecraft to execute and gain client-side execution on a hardened workstation, allowing us to continue our post-exploitation tactics. XSL Transform. It's beneficial to prepare multiple bypasses in the event one is blocked. In this section, we'll demonstrate a second way of obtaining arbitrary JScript execution while bypassing AppLocker through XSL transformation. The process of XSL transformation, or XSLT, uses extensible style sheet language, or XSL documents, to transform an XML document into a different format, such as XHTML. Part of the XSL transformation specification allows execution of embedded JavaScript code when processing the supplied XML document. Security researchers have discovered an XSL transformation attack that allows arbitrary code execution when triggered. To leverage this, we must first craft a malicious XSL document and put it on our Apache web server. As a proof of concept, we're going to launch a command prompt. Once the file is created, we must download it and invoke a transform to trigger the JScript code. This may be done through the WMI command line utility by specifying the verb get and the format switch, followed by the URL of the XSL file. Once the command is executed from a command prompt, a new command prompt is opened, proving that our JScript code executed. This application whitelisting technique can also be leveraged through a shortcut file that we provide to the victim. To weaponize this, we can modify the JScript code inside the XSL file to contain a .NET to JScript C# shellcode runner, or any other payload we desire. JScript and MSHTA. The MSHTA client-side attack vector is well known, but works best against Internet Explorer. As Internet Explorer becomes less used, this vector will become less relevant, but will nonetheless reinvent it to bypass AppLocker and execute arbitrary JScript code. First, we'll briefly describe the MSHTA attack and provide context for an AppLocker bypass. Microsoft HTML applications, or MSHTA, work by executing HTA files with the native mshta.exe application. HTML applications include embedded JavaScript, or VBS code, that is parsed and executed by mshta.exe. Since mshta.exe is located in C Windows System 32 and is a signed Microsoft application, it is commonly whitelisted. Because of this, we can execute our JScript code with mshta.exe instead of wscript.exe, and subsequently bypass application whitelisting. Let's create a very simple HTA file containing JScript code. When executed by mshta.exe, the JScript code inside both the head and the body tags will be executed. A command prompt will be spawned, and the mshta.exe window will be closed. When we save this code to a local file, and execute it from the command line, we observe that it does indeed bypass AppLocker. This effectively reinvigorates our JScript tradecraft. We can deliver this in a few different ways. For example, we could attach it to an email or HTML smuggle the file through a browser. Either way, the user must be tricked into running it to execute our code. In our case, we'll create a shortcut file and store our HTA file on our Apache web server. To create the shortcut file, we'll right-click the desktop on the Windows 10 victim machine and navigate to New Shortcut. In the new window, we'll enter the mshta executable path followed by the URL of the HTA file on our Kali machine. To create it, we'll click Next and name it. Once test.hta is transferred to our Kali machine, we can double-click the shortcut file to execute our JScript code. As a final step of this weaponization, we can bring back the JScript code generated with .NET to JScript and embed it in the HTA file to obtain a reverse shell by only sending the victim a shortcut file. Bypassing AppLocker with JScript. Throughout this course, we have primarily leveraged Microsoft Office and JScript files to obtain client-side code execution. Along the way, we have greatly improved our tradecraft to bypass endpoint protections, and we have found a way to reuse all of that tradecraft with Microsoft Office. Due to the scripting rules imposed by AppLocker, JScript code, which is not located in a whitelisted folder or whitelisted through a file hash or signature, will be blocked. For example, if we attach a JScript file to an email or deliver it through an HTML smuggling attack, the execution will be blocked by AppLocker, disrupting our attack. In the next sections, we'll reuse our JScript and .NET to JScript tradecraft and modify it to bypass AppLocker. Invoking the target, Part 2. We have managed to create a valid input file in XML format that will be processed by Microsoft Workflow Compiler and used to compile and load our C# code. Now we must finish the work and figure out how we can achieve execution of the newly compiled code. In internal compile from DOM batch, we find a check for classes that extend on the activity. Each located class will subsequently be instantiated to an object through the createInstance method by invoking the default constructor for the class. This means that the file containing code we provide must contain a class that inherits from the activity class of the System Workflow Component Model namespace and must contain the code we want to execute inside its constructor. We have now managed to reverse engineer and develop the required input files to achieve code execution. There is, however, one missing step. We determined that Microsoft Workflow Compiler required 2 arguments. The second command line argument is only used with the write compiler output method. Following that call, dnspy reveals the following. The argument is used as a file path, and content is written to it in XML format. Since we only care about obtaining code execution, we can simply pass a random file name as the second command line argument. This concludes our analysis, and we now have all the information we need. In summary, we must craft a file containing C# code, which implements a class that inherits from the activity class and has a constructor. The file path must be inserted into the XML document along with compiler parameters organized in a serialized format. To create this correctly serialized XML format, we'll take advantage of the serialize input to wrapper method in a PowerShell script. Once the file is generated, we make sure the student user is able to read the file. With everything in place, we can run the executable with the 2 input arguments. The output reveals that our efforts were successful. We executed arbitrary C# code. Excellent. In this section, we have completed our analysis and investigation of the chosen assembly, and in the process, created a working AppLocker bypass for managed code. The downside to this attack is that we must provide both the XML file and the C# code file on disk, and the C# code file will be compiled temporarily to disk as well. Despite these limitations, this simple code can be applied to any existing C# tradecraft. Invoking the target, Part 1. In this and the next section, we must finish our reverse engineering and create proof of concept bypass code. We've already found that the native Microsoft Workflow compiler application can be used to invoke the compile method with arguments supplied on the command line. The first command line argument is a file path, which must be parsed by the read compiler input method. We must inspect the read compiler input method to determine what the file format and content of the first command line argument should be. We previously found that read compiler input creates an XML reader stream, after which the read object method is used to deserialize the data of the stream and return it as the type compiler input. To build upon this knowledge, we must understand both the content of the serialized XML file and the deserialization process. Read object makes use of the data contract serializer method to aid in the serialization. This is in line with the MSDN documentation, which reveals that a similar serialization process would use data contract serializer along with write object. At this point, to understand how to successfully serialize our input, we could either reverse engineer all the required flags, or we could attempt to locate code related to serialization inside the assembly. We choose to do the latter and press Ctrl-Shift-R to analyze data contract serializer. Which tells us that it is only used in two methods. Besides the read compiler input method we're currently investigating, data contract serializer is only used in serialize input to wrapper, which has a very promising name. Selecting the method name reveals its body. The code shows a serialization process similar to the one encountered in compiler input. This code is perfect for our purposes, since it serializes a data object of type workflow compiler parameters into an XML file on the file system. Since we have found a method that directly serializes into our desired format, we can simply create a PowerShell script that calls it. Because the method is private, we must use reflection to locate it with getMethod. With the method resolved, we must determine which arguments it accepts. The first are the workflow compiler parameters. Fortunately, the type is public, meaning we can simply instantiate an object of this type. The second argument is an array of strings containing file paths. Once we've set up the argument values, we can call the method through reflection with the invoke method. After executing the code, we can dump the contents of the generated file to view the serialized content. We notice two things from the contents of the file. First, the file path we supplied has been embedded into it and will be used with the call to compile once the file is deserialized. Second, quite a few compiler flags have been added, but at this time we do not know if the values they contain will lead us down the correct code path in order to process and execute an arbitrary malicious assembly file. With an understanding of how we can generate an input file that will be deserialized correctly by Microsoft Workflow Compiler, we must return to dnSpy. Our goal is to determine what file format and content the file name embedded in the XML file should have, and which compiler flags are required to reach the compilation, loading, and subsequent execution sections. After returning to the main method of Microsoft Workflow Compiler in dnSpy, we find that the next call is to compile, where the deserialized parameters and file names are supplied as arguments. We follow the call and first notice null checks on the input values, after which various actions are performed depending on the given parameters. The output assembly parameter is only checked and modified if the generate in memory flag is set. From our generated XML file, we find that it is set to false by default. The output assembly parameter is likely the file name and path of the generated assembly file, and if it does not exist, the compilation will likely fail. Because of this, we must update our PowerShell script to set generate in memory to true. After parsing the parameter, we follow the call into the compile method of the Workflow Compiler internal namespace. Where we find the following for each loop. Very interestingly, we find a comparison on the file name against the XOML extension, which is used by the relatively undocumented Extensible Object Markup Language file format. This is essentially an XML document that can contain embedded code. File names with XOML extensions will be added to the array variable, while file names with other extensions will be added to array2. Since XOML files can contain embedded code, we can assume that this is a required file, but we must continue our analysis to prove this. From our investigation in the previous sections, we located the code path to trigger the compilation and loading of the assembly, and discovered that we must trace into the call to generate local assembly, which was supplied the arguments. Once inside the call, we can inspect the function prototype of generate local assembly to gain a better and somewhat contradictory understanding of the arguments. From the argument names, we find that the files with an XOML extension are called files, while those with any other extension are called code files, which leads us to believe we should avoid XOML files. This seems contradictory to the previous analysis. To understand this, we'll turn our attention to the first call inside the method, which is to generate code from file batch. This method is given the files variable, which contained the XOML files as its first argument. If we were to reverse engineer the method, we would discover rather extensive code designed to parse the files and detect and extract embedded code. Still inside generate local assembly, generate code from file batch returns the embedded code from the XOML files into the value variable. Near the end of the method, we find the following code block. The files containing code that were extracted from an XOML file are added into the ArrayList2 variable, and those without this extension are added into the ArrayList3 variable. In the second to last line of code, the extracted code is converted to files and added to ArrayList3. In effect, this means that we do not have to worry about the partially undocumented XOML format and can instead simply provide a file containing C# code with an arbitrary extension. To summarize what we've discovered so far, Microsoft Workflow Compiler accepts two arguments. The first must be the path to an XML file containing compiler flags, and the path to a file containing C# code. The C# file will be compiled and loaded into memory without restrictions. Give me code exec. In this section, we'll continue our reverse engineering session to discover how we can obtain code execution under specific circumstances. During our analysis in the previous section, we followed the code path starting from the compile method of the Workflow Compiler internal namespace. That code trace led us to generate local assembly, which in theory should allow us to compile and subsequently load an arbitrary assembly. Now we'll analyze internal compile from DOM batch, which follows after the generate local assembly call. Before following the call into internal compile from DOM batch, we notice that generate local assembly returns the newly compiled and loaded assembly inside the local assembly property of the parameters variable. A reference to the assembly is subsequently stored in the type provider variable. When we follow the call into internal compile from DOM batch, we're led into the XOML compiler helper namespace. After some argument validation and variable initialization, we find the following for each loop. The loop iterates over all classes in the previously compiled file as given by the reference stored in the type provider variable. For each iteration, it checks for classes which inherit from System Workflow Component Model activity and are not abstract. Assuming at least one such class exists, we go into the loop where the createInstance method is invoked, which instantiates an object of the given type. When an object is instantiated from a class, the defined constructor is executed. Our hypothesis is that the compile method of the compiler workflow compiler namespace is called with the path of a file containing C# source code given as an argument. After several iterations of validation and parsing, the provided .NET code is compiled into an assembly, loaded into memory, and if it contains a non-abstract class, which inherits from the activity type, an object is instantiated. If we're able to provide our desired code as part of the constructor for that class, we can obtain arbitrary code execution and bypass AppLocker. This concludes the second stage of reverse engineering. We have located a theoretical path that will lead to code execution. Now we must discover how to provide proper input to the constructor. Reverse engineering for load. Let's begin the process of locating a load call inside System Workflow Component Model DLL. Since we're reverse engineering managed code, we'll need a new tool. We'll use dnSpy, which is the tool of choice for disassembling and performing reverse engineering on compiled .NET code. This tool has been installed on the Windows 10 victim machine, and a shortcut has been placed on the taskbar. Thanks to application whitelisting, we must launch dnSpy as an administrative user. After launching dnSpy, we'll navigate to File, Open, browse to the target assembly, and select Open. This will load System Workflow Component Model DLL, automatically decompile it, and add it to the Assembly Explorer. Based on its name alone, the System Workflow Component Model Compiler namespace is worth investigating, since compilation often involves loading a file or data. Expanding the namespace reveals the Workflow Compiler class, which contains the compile method. Based on the class and method name, this seems a good starting point for our analysis, as we're trying to leverage existing functionality within the code base to compile our own C# source code and load it into memory. There are multiple steps we have to perform as part of this analysis. First, we'll begin by determining if the compile method does indeed lead to compilation of source code. If so, we must ensure that we're able to invoke this function and supply the source code. Finally, we must determine if and how the code is executed. The code begins with various argument checks and eventually executes these statements. Line 57 calls into the internal compile method in the Workflow Compiler internal namespace. If we click on the method name, dnSpy will jump to that code and display it. The initial instructions validate the arguments. Further down in the code, we find the following instructions. The generate local assembly and internal compile from DOM batch methods are especially interesting, given that we're searching for a code segment responsible for compiling managed code. Let's start with generate local assembly and follow it with dnSpy. Eventually, we reach the following code. Based on the name alone, the compile assembly from file method from the code DOM provider namespace is worth investigating. Following the call to this method reveals that this is a small wrapper method for compile assembly from file batch. At this point, we are quite deep into the code. Let's take a moment to investigate this method to validate that we're on the right track. MSDN confirms that compile assembly from file batch does indeed compile an assembly, as the name suggests. Good, we're headed in the right direction. Let's continue. If we follow the call into compile assembly from file batch, we only find the method definition. There's no function implementation because this is part of an interface. To find the implementation of the interface from the system code DOM compiler namespace, we can right-click the method name and select Analyze, or press Ctrl-Shift-R, which will open a pane in the lower right-hand side of the application. We can expand this by clicking Implemented By. Now we can select the second entry to find the implementation of compile assembly from file batch. The method validates the supplied file paths and then calls from file batch. Within from file batch, we find a call to the compile method, where the C# code supplied through file names is finally compiled. Further on, after the source code has been compiled and stored in the array variable, we locate the code we have been searching for. The code shown loads the now compiled assembly with assembly load. Very nice. The only caveat is that this call is only triggered if the file integrity property is not enabled. Let's investigate file integrity to determine if it will be enabled in our scenario. Matt Graber writes on his blog that when the file integrity is enabled property is evaluated, a call is made to WLDP is dynamic code policy enabled, which will only return true if WDAC is enabled and certain specific properties are enforced. Since we're only dealing with AppLocker, this does not apply to us, and this code path will execute. At this point, we have made significant progress reverse engineering the System Workflow Component Model DLL assembly. We found a code path that compiles and loads C# code based on given input files. Before we go any further with the analysis, we must ensure that we're actually able to invoke the compile method from the Workflow Compiler class inside System Workflow Component Model DLL. Additionally, we must determine if we're able to control the arguments provided to it. To find an executable that invokes the compile method, we'll navigate back to it in dnspy. We'll right-click the method name and select Analyze. Next, we'll expand the Used By section, which reveals two entries, including Microsoft Workflow Compiler Program Main. This is the main method of an executable, which means the compile method is called directly from this .NET application. Double-clicking on the entry will open the relevant assembly in dnspy, which will automatically present its code. Additionally, the Assembly Explorer neatly displays the application name as Microsoft Workflow Compiler. To locate this file on disk, we can right-click on the assembly in Assembly Explorer and choose Open Containing Folder, which opens the directory in File Explorer. Alternatively, we could hover over the assembly name in Assembly Explorer to display the path name. At this point, we have found a way to trigger the compile method directly from a native and signed Microsoft application. We must also determine if the arguments supplied to compile come directly from Microsoft Workflow Compiler. We'll start this analysis from the main method of Microsoft Workflow Compiler.exe and inspect the arguments it accepts. This reveals that two arguments must be passed, and that only the first is used with the compile method. The contents of the first argument are parsed by the read compiler input method, which returns an object that contains compiler parameters and file names. The information discovered here is very enlightening. It tells us that any input to compile should be under user control. However, the input does go through some sort of validation via read compiler input. If we follow read compiler input, we find that the content of the file passed as an argument is read into a stream, after which it is used to create an XML reader stream. This shows us that we must supply an XML file as the first argument to Microsoft Workflow Compiler. After the XML reader stream is created, the read object method is used to deserialize the data of the stream and return it as the compiler input type, which is a custom type defined inside Microsoft Workflow Compiler. If we click on the type, we find that it contains only two elements, parameters and files. At this point, it seems that we should be able to pass a file of our own choosing to Microsoft Workflow Compiler as the first argument. However, the file must contain serialized XML data. While it's not yet clear what the contents of the file should be, nor how the deserialization works, we have found that we should be able to trigger execution of compile with arguments under our control. There is still much work left to do in this analysis. Simply compiling C# code and loading an assembly into memory is not enough to acquire code execution. In the next section, we must continue our reverse engineering to determine whether or not the newly compiled assembly is actually executed. Locating a target. To begin, let's discuss the components of an AppLocker bypass. Our ultimate goal is to execute arbitrary C# code via a whitelisted application, which means our target application must either accept a precompiled executable as an argument and load it into memory, or compile it itself. In addition, the target application must obviously execute our code. Either way, the whitelisted application must load unsigned managed code into memory. This is typically done through APIs like load, load file, or load from. The first step in this process is to locate native compiled managed code that performs these actions. While it may seem logical to simply scan each assembly for one of these loading methods, the compilation and loading processes are typically performed by nested method calls inside core DLLs. Still, we could scan a compiled assembly for references to either of the previously mentioned methods through the dnlib external library, or with the load methods scanner developed by security researcher Matt Graber. Although this approach automates the search process and scales well, developing the test harness requires significant preparation. Alternatively, we could reverse engineer assemblies which reside in whitelisted locations in search of the code segments that either load precompiled managed code or use source code, which is compiled as part of the processing. Once identified, these code segments must execute the code we provide after it is loaded into memory. In the following sections, we'll leverage this second approach, focusing on the System Workflow Component Model DLL assembly, which is vulnerable to a relatively new AppLocker bypass. This assembly is located in a Windows subdirectory, which is whitelisted by AppLocker's default path rules. Additionally, the assembly is signed by Microsoft, so it is whitelisted through a default publisher rule. Let's reverse engineer this assembly, locate the specific logic we'll use to bypass AppLocker, and finally, weaponize it. Reflective injection returns. In an earlier module, we used the invoke reflective PE injection PowerShell script to inject an unmanaged Meterpreter DLL into a process with reflective DLL injection. However, in a previous section, we enabled AppLocker DLL rules to block untrusted DLLs. Let's try to leverage install-util to bypass AppLocker and revive the powerful reflective DLL injection technique. First, we'll generate a 64-bit Meterpreter DLL and host it on the Apache server on our Kali machine. We'll also make sure the invoke reflective PE injection.ps1 script from C tools is on the Apache server to simulate the full attack scenario. Next, we'll modify the CMD variable inside the constrained language mode bypass from the C# application developed in the previous sections. Our goal is to download the Meterpreter DLL into a byte array. Determine the process ID of explore.exe for the DLL injection, and download and execute the invoke reflective PE injection script. Since we passed the script on a single line, we use the semicolon command terminator to supply multiple commands at once. Once we compile and execute the C# application through install-util, it generates a reverse shell, proving that the unmanaged DLL successfully loaded, bypassing AppLocker's DLL rules. PowerShell CLM bypass. In the last section, we bypassed constrained language mode in PowerShell, but ended up needing the ability to bypass the AppLocker executable rules for a C# application. In this section, we'll demonstrate how native Windows applications can be abused to bypass AppLocker by fooling the filter driver. In this section, we'll leverage install-util, a command line utility that allows us to install and uninstall server resources by executing the installer components in a specified assembly. This Microsoft-supplied tool obviously has legitimate uses, but we can abuse it to execute arbitrary C# code. Our goal is to reintroduce our PowerShell shellcode runner Tradecraft in an AppLocker-protected environment. To use install-util in this way, we must put the code we want to execute inside either the install or uninstall methods of the installer class. We are only going to use the uninstall method, since the install method requires administrative privileges to execute. Using the MSDN documentation as a guide, we can build the following proof of concept. There are a few things to note about this code. First, the system configuration install namespace is missing an assembly reference in Visual Studio. We can add this by again right-clicking on References in the Solution Explorer and choosing Add References. From here, we'll navigate to the Assemblies menu on the left-hand side and scroll down to System Configuration Install. Once the assembly reference has been added, the displayed errors are resolved. Although our code uses both the main method and the uninstall method, content in the main method is not important in this example. However, the method itself must be present in the executable. Inside the uninstall method, we can execute arbitrary C# code. In this case, we'll use the custom run space code we developed in the previous section. With the executable compiled and copied to the Windows 10 victim machine, we'll execute it from an administrative command prompt. As shown in the output, the main method executed. If we run it from a non-administrative command prompt, AppLocker blocks it. To trigger our constrained language mode bypass code, we must invoke it through install-util with /logfile to avoid logging to a file, /log to console equals false to suppress output on the console, and /u to trigger the uninstall method. The output shows that install-util is allowed to execute. It started the .NET Framework installation utility, and the test.txt output shows that our PowerShell script executed without restrictions. Excellent. There is, however, a slight issue. The compiled C# file has to be on disk when install_util is invoked. This requires two distinct actions. First, we must download an executable, and secondly, we must ensure that it is not flagged by antivirus, neither during the download process nor when it is saved to disk. We could use VBA to do this, but it is simpler to rely on other native Windows binaries, which are whitelisted by default. To attempt to bypass antivirus, we're going to obfuscate the executable while it is being downloaded with base64 encoding and then decode it on disk. We'll use the native certutil tool to perform the encoding and decoding, and bitsadmin for the downloading. By using native tools in unexpected and interesting ways, we will be living off the land. There are a couple of steps involved in setting this up, so let's take them one at a time. First, we'll use certutil on our Windows 10 development machine to base64 encode the compiled executable. This is done by supplying the encode flag. Now that the binary has been base64 encoded, we'll copy it to the web root of our Kali machine. And ensure that Apache is running. Then we'll use bitsadmin to download the encoded file. To download the file, we'll specify the transfer option, along with a custom name for the transfer and the download URL. With the file downloaded, we can decode it with certutil-decode. We executed the decoded executable with install_util and bypassed both AppLocker's executable rules and PowerShell's constrained language mode. Since all of these commands are executed sequentially, we can combine them on the command line through the && syntax. Our bypasses were again successful. Very nice. In this section, we further developed our tradecraft to allow arbitrary C# execution and unrestricted PowerShell execution despite application whitelisting. We are now able to reuse our existing client-side code execution techniques from Microsoft Office. Custom run spaces. Before exploring constrained language bypass techniques, we must first explore the various components of a typical PowerShell implementation. PowerShell.exe is essentially a GUI application, handling input and output. The real functionality lies inside the Managed System Management Automation DLL, which PowerShell.exe calls into to create a run space. It's possible to leverage multi-threading and parallel task execution through either jobs or run spaces. The APIs for creating a run space are public and available to managed code written in C#. This means we could code a C# application that creates a custom PowerShell run space and executes our script inside it. This is beneficial since, as we'll demonstrate, custom run spaces are not restricted by AppLocker. Using this approach, we can construct a constrained language mode bypass to allow arbitrary PowerShell execution. To begin, let's turn to our Windows 10 development machine to create a new C# console app project. In this project, we'll create a run space through the create run space method of the System Management Automation Run Spaces namespace. Unfortunately, Visual Studio cannot locate System Management Automation Run Spaces. To resolve this, we must manually add the assembly reference. First, we'll right-click the References folder in the Solution Explorer and select Add Reference. In most cases, the reference can be found in existing assemblies, but in this particular case, we need to specify a file location instead. To do this, we'll select the Browse button at the bottom of the window and navigate to the relevant directory. Where we'll select System Management Automation DLL. After adding the assembly reference, the previous errors are resolved. Now we can dig into the code. Calling create run space creates a custom run space and returns a run space object. We can invoke the open method on this object, after which we may interact with the custom run space. With the custom run space created, we can instantiate a PowerShell object and assign the run space to it, which allows us to pass and invoke arbitrary PowerShell commands. This is implemented through the create method of the PowerShell class. The final line of code will set the run space property to our custom run space. At this point, we have created a custom run space and associated it with a PowerShell object. Now we're ready to pass in a command or script and execute it. As a proof of concept, we'll simply write the contents of the execution context session state language mode variable to a file, so we can verify the language mode of the custom run space. The PowerShell script is added to the pipeline through the add script method, after which the invoke method is used to execute the script. Finally, the close method is called to close the custom run space for cleanup. Before compiling the project, we'll switch from debug to release mode and select 64-bit for compilation. After compilation, we'll copy the executable to the Windows 10 victim VM, and execute it. AppLocker blocks our C# executable because we executed it from a non-whitelisted directory. Let's copy the executable into a whitelisted directory to verify our constrained language mode bypass. Our PowerShell script executed without restrictions inside the custom run space, and our code achieved the desired goal. Good. Additionally, we did not use PowerShell.exe, which means that even if an AppLocker deny rule was configured to block its execution, we could still use this method to run arbitrary PowerShell scripts. As an expanded use case, let's leverage the custom run space to fetch and execute the PowerUp PowerShell Privilege Escalation Enumeration script. We'll download the script and copy it to our Kali Machine's Apache web server, and update the C# application to invoke inside the custom run space. Once the C# project has been modified with the new script and recompiled, we can execute the C# executable and enumerate possible avenues of privilege escalation. The power of custom run spaces allows us to reuse all our previous PowerShell-based tradecraft. However, we're still hindered by AppLocker's C# executable rules. In the next section, we'll solve this problem by using a technique called living off the land, in which we misuse a native Windows application. PowerShell Constrained Language Mode. The PowerShell execution policy restricts the execution of scripts, but this is a weak protection mechanism, which can be easily bypassed with the built-in bypass execution policy. However, the more robust language modes avoid execution of code like our shellcode runner and operates at 3 distinct levels. The first and default level, full language, allows all commandlets and the entire .NET framework, as well as C# code execution. By contrast, no language disallows all script text. Restricted language offers a compromise, allowing default commandlets but heavily restricting much else. These settings are relatively uncooperative. For example, it would be difficult to allow administrative execution while allowing execution of scripts we trust and blocking scripts belonging to a user, malicious or otherwise. To address this, Microsoft introduced the Constrained Language Mode, or CLM, with PowerShell version 3. When AppLocker, or Windows Defender Application Control, is enforcing whitelisting rules against PowerShell scripts, Constrained Language Mode is enabled as well. Under Constrained Language Mode, scripts that are located in whitelisted locations, or otherwise comply with a whitelisting rule, can execute with full functionality. However, if a script does not comply with the rules, or if commands are entered directly on the command line, Constrained Language Mode imposes numerous restrictions. The most significant limitation excludes calls to the .NET Framework, execution of C# code, and reflection. To demonstrate this, let's open a PowerShell prompt in the context of the student user, and attempt to invoke the .NET Framework. As evidenced by the warning, we cannot access the otherwise simple cosine function in the math namespace of .NET. This warning is indicative of Constrained Language Mode. The language mode of the current PowerShell session or prompt is always stored in the execution context session state language mode variable, which can be displayed as follows. In contrast, let's open a second PowerShell prompt with administrative privileges in the context of the OffSec user, and dump the contents of the same variable. Obviously, this is our preferred language mode, as it is unrestricted, allowing us to reuse all of our previous tradecraft. However, in the next section, we'll dig deeper into .NET and develop code that will bypass Constrained Language Mode. Bypassing AppLocker with PowerShell. In previous sections, we executed simple bypasses. In the remaining sections, we'll investigate advanced and increasingly complex bypasses and reuse previously developed tradecraft that bypasses non-standard AppLocker rule sets. Our previously developed tradecraft relied heavily on PowerShell, which, as previously demonstrated, can easily bypass detection mechanisms like AMSI. In this section, we'll analyze the various restrictions AppLocker places on PowerShell and demonstrate bypasses. Alternate data streams. So far, we have demonstrated various ways of bypassing AppLocker if the rules are not appropriately configured. In this section, we'll work through a slightly more advanced bypass that abuses a feature of the Windows file system itself. The modern Windows file system is based on the NTFS specification, which represents all files as a stream of data. While the inner workings of NTFS are complex, for the purposes of this module, it's important to simply understand that NTFS supports multiple streams. An alternate data stream is a binary file attribute that contains metadata. We can leverage this to append the binary data of additional streams to the original file. To demonstrate this, we'll create a small JScript file. We'll save this as test.js in the student user's home directory. Since we have AppLocker scripting rules in place, we cannot execute it in its current location. However, if we can find a file in a trusted location that is both writable and executable, we could write the contents of this script to an alternate data stream inside that file and execute it, bypassing AppLocker. For example, TeamViewer version 12, which is installed on the Windows 10 Victim machine, uses a log file that is both writable and executable by the student user. We can use the native type command to copy the contents of test.js into an alternate data stream of the log file with the colon notation. We'll use dir/r to verify that the JavaScript code was written to the alternate data stream. The output indicates that the script has been written to the alternate data stream. Now we must execute it. If we simply double-click the icon for the log file, it would open the log, which is the primary stream, in Notepad as a standard log file. However, if we execute it from the command line with wscript, specifying the alternate data stream, the JScript content is executed instead. In this case, the JScript code executed and opened a new command prompt despite the AppLocker script rules. Bypass with DLLs. In the previous sections, we relied on basic AppLocker rules, ignoring rule types associated with dynamic link libraries. The default rule set doesn't protect against loading arbitrary DLLs. If we were to create an unmanaged DLL, we would be able to load it and trigger exported APIs to gain arbitrary code execution. Let's demonstrate this with an unmanaged DLL. We'll use a simple unmanaged DLL main function, along with an exported run function that opens a message box when executed. This code has already been compiled and saved as testdll.dll under the tools directory on the Windows 10 Victim VM. To load an unmanaged DLL, we'll use the native RunDLL32 tool, which accepts the full path to the DLL along with the exported function to execute. Although this is basic code, it demonstrates that DLLs are not restricted by the current AppLocker rules. We can, however, enforce DLL whitelisting with AppLocker, again through the local group policy editor. Let's do that now. Reopening the rule enforcement window in the group policy editor, we'll click the Advanced tab. This presents a warning about system performance issues related to DLL whitelisting enforcement and offers the option to enable it. After checking Enable the DLL Rule Collection and clicking Apply, we'll return to the original Enforcement tab, which presents a new entry related to DLLs. Here, we'll enable DLL enforcement and return to the main AppLocker configuration window. A DLL Rules section now allows us to create default rules. Once everything is configured, we'll once again execute gp update/force from an administrative command prompt to activate the settings. To test the configured rules, we'll attempt to load test.dll.dll with run DLL32 again. This presents the AppLocker error message. The DLL has been blocked. Unless the default DLL enforcement rules have been modified, we could bypass whitelisting by copying test.dll.dll into C Windows Tasks. Trusted folders. The default rules for AppLocker whitelist all executables and scripts located in Program Files, Program Files x86, and Windows directories. This is a logical choice, since it's assumed that non-admin users cannot write executables or scripts into these directories. In this section, we'll put this assumption to the test as we construct our first, albeit very simple, AppLocker bypass. In theory, we should be able to execute a program or script in a subdirectory that allows both write and execute. If we can find writable and executable folders on a development machine, we can reuse the bypass later on a compromised machine which has the same rules applied. For this test, we'll use an administrative command prompt to avoid potential AppLocker restrictions. To locate user writable folders, we'll use Access Check from sysinternals, which is located in C Tools sysinternals suite on our Windows 10 victim VM. We'll search C Windows with Access Check, using -W to locate writable directories, U to suppress any errors, and S to recurse through all subdirectories. Surprisingly, the output returned by this command is quite lengthy. It contains several writable subdirectories. Next, we must determine if any of them are also executable. We'll start with the native iCackles tool from an administrative command prompt to check each of the writable folders. For example, we'll first check the Windows Tasks directory. The output indicates the RX flag associated with the NT Authority Authenticated Users group is set for the Windows Tasks directory, meaning that any user on the system will have both read and execute permissions within the directory. Based on the output of these tools, the student user will have both write and execute permissions within this directory. To test this out, we'll copy calc.exe to the Windows Tasks directory and execute it. The program runs, indicating that we have bypassed the default AppLocker application whitelisting rules. Basic bypasses. So far, we have walked through the different types of rules and the categories of file types protected by AppLocker. We have configured our Windows 10 Victim VM with the default AppLocker rules, and we're ready to explore various bypasses. In the following sections, we'll specifically focus on a variety of simple bypasses that stem from the relatively poor configuration enforced through the default rules. We'll also demonstrate bypasses that leverage limitations of AppLocker itself. AppLocker, Setup, and Rules. There are three primary AppLocker rule categories, which can be combined as needed. The first and most simple rule is based on file paths. This rule can be used to whitelist a single file based on its file name and path, or recursively include the contents of a directory. The second rule type is based on a file hash, which may allow a single file to execute regardless of the location. To avoid collisions, AppLocker uses a SHA-256 Authenticode hash. The third rule type is based on a digital signature, which Microsoft refers to as a publisher. This rule could whitelist all files from an individual publisher with a single signature, which simplifies whitelisting across version updates. To get started with a simple case study, we'll set up some basic AppLocker whitelisting rules. In order to simplify our testing, we'll log into the Windows 10 Victim as student, since administrators will be exempt from the rules we'll create. Let's open an administrative command prompt. Enter the OffSec user credentials. And launch gpedit.msc, the GPO configuration manager. In the Local Group Policy Editor, we'll navigate to Local Computer Policy, Computer Configuration, Windows Settings, Security Settings, Application Control Policies, and select the AppLocker item. The rule creation and configuration process consists of several steps. First, we'll click Configure Rule Enforcement to open the properties for AppLocker. In the Properties menu, we can enable AppLocker rules for executables, Windows installer files, scripts, and packaged apps. This will set 4 rule properties which enable enforcement for 4 separate file types. The first property relates specifically to executables with the exe file extension, and the second relates to Windows installer files, which use the MSI file extension. The third property relates to PowerShell scripts, JScript scripts, VB scripts, and older file formats using the CMD and BAT file extensions. This property does not include any third-party scripting engines like Python, nor compiled languages like Java. The fourth property relates to packaged apps, also known as Universal Windows Platform or UWP apps, which include applications that can be installed from the Microsoft App Store. For each of these 4 categories, we will select Configured. In addition, we can choose to enforce rules, to enable the rule and enforce whitelisting, or audit only, which will allow execution and write an entry to the Windows event log. We'll configure AppLocker to enforce rules for all 4 categories. Click Apply and OK to close the window. Next, we must configure rules for each of these 4 categories. We'll do this from the options in the lower part of the main window, titled Overview. We'll first click Executable Rules to open a new window where we can enter the whitelisting rules related to each specific property. Right-clicking the pane presents 2 options for rule creation. The first is Create New Rule, which will let us define a custom rule based on any of the 3 rule types. The second, Create Default Rules, will automatically apply the default AppLocker rules. We'll begin with the default rules, which will be easier to work with. As we progress through the module, we'll add additional rules to further harden the box. Once we've chosen to apply the default rules, they will be added to the pane. This should block all applications except those explicitly allowed. Specifically, the 2 first rules will allow all users to run executables in C program files, C program files x86, and C Windows recursively, including executables in all subfolders. This allows basic operating system functionality, but prevents non-administrative users from writing in these folders due to the default access rights. The third rule allows members of the administrative group to run any executables they desire. The other 3 categories have similar default rules. We'll enable them to configure basic application whitelisting protection on our Windows 10 Victim VM. Once we have created all the default rules, we must close the local group policy editor and run gpupdate/force from the admin command prompt to refresh the active group policies. Now that AppLocker is configured and enabled, non-admin users should not be able to execute any executable or script outside allowed directories. To test this, we'll start a command prompt as student in a non-admin context. We'll copy the native calc.exe executable from the Windows System 32 directory into the current directory and attempt to execute it. The error was generated by AppLocker, which blocked execution. AppLocker logs each violation in the Windows event log. To view this message, we'll open Event Viewer, press Windows R, enter Event Viewer, navigate to Applications and Services Logs, Microsoft, Windows, AppLocker, and select EXE and DLL. The error reveals that execution of calc2.exe has been blocked.